All right, so let's start with our work on rate of reaction. First, we need to revise a couple of things because we need to make sure we're all on the same page. First of all, let's look again at the difference between an endothermic and exothermic reaction. You did do this in grade 11. So remember, during a reaction, energy is absorbed to break chemical bonds. That's when we break it up. That's what happens to the reactants. And then energy is released when we form chemical bonds. So that's when we make the products, okay? The difference between these two tells us whether energy is given off or taken in during the reaction, and it then will tell us exactly whether it's an exothermic or endothermic reaction. So, in an exothermic reaction, the important thing to remember here is that energy is always released. So, the energy that's given off is more than the energy that's taken in, and delta H is smaller than 0. In other words, delta H is negative, okay? That's the heat of reaction. Secondly, and it releases energy. An endothermic reaction absorbs energy, and delta H is now greater than 0, so it's positive. That's very, very important, okay? And knowing whether delta H is positive or negative is really going to help us later on. Remember, delta H, which is also known as enthalpy, all right, that's the term we give it, or the heat of reaction, is the energy that is absorbed or released in a chemical reaction, so it refers to both. Then, when it comes to determining the rate of a reaction, so now we want to know how fast or how slow the reaction goes, we can measure it, and this is general, okay? So, either the rate of reaction can be seen as the change in concentration of the reactant. That square bracket means concentration. It's a new thing for you. You're going to see it often. Or it can be the change in concentration of the products over time. So it's about the time. Now, the thing here is that our units aren't set. So time doesn't have to be in seconds. It could be in minutes or hours or days, depending on what the reaction is. And even though we say in general that it's the change in concentration, it can be in other quantities. So we can also measure the change in volume, which we'll see now. So I can look at the change in the mass rather than the concentration. And I can also look in the change in volume. All right, so I can measure this in concentration, mass, or volume per unit time. So when it comes to measuring the calculating rate of reaction, we have to look at the reaction specifically, okay? So we have to look at what is happening inside the reaction. All right, so color change and precipitation formation is very difficult at school level to do a calculation with. So you're never going to have to do a calculation with it, but we are going to talk a little bit later on how we would measure that. Okay, so how do we represent a rate of reaction? So the rate of reaction is by a graph, okay? Just like everything else, we're going to do a graph, which means you need to be able to interpret it. So very important things to remember. Number one, products are always made. We always increase the amount of product, and we usually start with no product, okay? Reactants are used up, so their amount must decrease. They may be all used up, they may not. It depends on the reaction. So, if we look at my general graph here, now what we really should do here is the rate graph should start at time 0, we have lots and lots of product, and at time 0, we have, reactant, and at time 0, we have no product. This is important. Then the reaction proceeds, okay, and we make lots of product, and we use up reactants. Now, the reactants graph could end up ending on the time axis if it all gets used up. So, in other words, if it all gets used up, there we're talking about the limiting reactant. If it doesn't get used up, just pretend you can read what I just wrote, then this would have to be my reactant that's in excess. Okay, we don't often look at this with the reactant in excess. We rather look at it when the reactant's used up, because once the reactant is used up, we can tell the reaction is stopped. if we're looking at the products, once the products become constant, so this graph becomes horizontal, then we're not making any more products, the reaction has stopped. Okay? The gradient of the graph is an indication of the rate of the reaction. So the faster it's going, the steeper the graph, okay, which we're going to look at here. So if we look at for the reactants, this is concentration, so we're using up. Don't worry about the fact that it hasn't didn't start on the y-axis, really doesn't matter. But we always use up the reactants, so it's decreasing, and you can see it's getting small, less and less and less. The rate of reaction is measured by calculating the gradient. Now, we aren't going to look at using a tangent. We're not going to look at using a calculus method. We're really going to be looking at averages, because you are not required to be able to calculate the gradient of a curve, okay? But what I do need you to see here is that the gradient's constantly changing. It's a curve. The gradient at the beginning is steepest because we have lots of reactants, and if we have lots of reactants, then we're going to have a very fast reaction. So the concentration of the reactants is very high. The gradient becomes less steep because we're using up the reactants, and it becomes lower and lower and lower. Okay, so it starts off quickly and ends up going slower and slower and slower till eventually the reaction stops. We can see the same thing with the concentration of the product, so we need to remember that the product is made. So at the beginning, there's no product. Very important. The gradient is steeper at the beginning, just like with the reactants, because the reaction is fast. The gradient becomes less steep as the reaction goes on, because we're using up the reactants. There's less and less available for it to happen. Eventually, it will become parallel. This is very important. This really should be more of a parallel line, because the reaction is complete. We've stopped making product. Okay? Now, you need to look at activity 1 on page 203. The memo is on Teams. The second part, so unit 2 now, is the mechanism of reactions. So, we need to look at collision theory. In collision theory states for us that for a reaction to occur, first of all, they must collide. You did this in grade 11. But colliding is not enough. They must be effective. So we've got to talk about effective collisions. How is a collision effective? Well, there must be sufficient energy, and they must collide with the correct orientation. So it's just not enough to collide. They've got to collide fast enough, and they've got to collide in the correct way. Okay? If one of these are not correct, the reaction will not happen. So, for example, if we have incorrect orientation, I want to create, okay, so if I look at this, when these two collide, I can't get, they're going to go back to their original, just the two blue and the two red, whatever they are, okay, whichever two diatomic elements they are, it doesn't matter. It doesn't matter if this collision has sufficient energy. It's not a correct collision, all right? They're not hitting each other in the correct way. However, if they now collide in the correct way, so now they collide with each other, they're happy this collision is the correct orientation, they can create the product, but they must collide with sufficient energy. If that's missing, doesn't matter if they're in the correct orientation. So, that gets us to activation energy. Activation energy is the minimum energy. That's what the sufficient energy is. That's the minimum energy required for the reaction to take place. That is very, very, very important. Okay? Because without that, it doesn't matter. Like we've said, it honestly does not matter how long or how the orientation is. That's irrelevant. Okay? Because they're not the correct, they don't have enough energy. Remember, you've done energy profiles. Okay? Energy potential graphs. This is my activation energy. It's taken from the energy the reactants have to the energy of the activated complex. Now, the activated complex, if you recall, it's a good word, from grade 11, is a temporary, unstable, high energy complex, it's where all the atoms are there, and it's a transition state where either the atoms will now form the products or they'll form the reactants for whatever reason, okay? We can't do anything with the activated complex, we cannot take it out. The reactants have a certain amount of energy, the products have a certain amount of energy, that is the nature of the reactants. The delta H, my enthalpy change, comes from products minus reactants, which is why it's negative with a exothermic reaction, and the activation energy is set. For an endothermic reaction, okay, the products end up with more energy than the reactants. The activation energy is still from the reactants to the activated complex. In this case, products minus reactants, high energy minus low energy gives you a positive value. Nice and easy. You've seen this. You did this in grade 11. So, the speed of the reaction, and it's a combine to these, okay? It really is about the number of, and in fact, we could take this out. We can really say number of, not there, we're going to put it here, number of effective collisions per unit time. So, it's not just about the number of collisions, about how many of those collisions are effective. Effective means that they turn into products. Effective means they make the product. Okay? Now, here you may need to watch this part a couple of times. Okay? Because now we're going to go into something new. And that's the energy in the Maxwell-Boltzmann curve. It actually should be called a distribution curve. It's a statistical curve. You've done something like this somewhere in your maths career. I really promise you have. So what this graph does, and it's a little different to what you used to, this here is not total number of particles. It's a number, okay? If I calculated the area under this graph, essentially, I get the total number of particles, because what this graph is telling me is if I look over here, this number of particles in my system, which is only part of the number, has this value of kinetic energy. In the system, the particles have, some particles have lots of energy, which is over here. Some particles have very little energy, okay? Some particles, a high proportion of the particles have a certain energy, which represents the average kinetic energy. This is what gives me the temperature of my system, okay? So this peak represents the temperature because it's the biggest number of particles with that kinetic energy. There's a couple of things we have to note. Number one, that point there tells me we have 0 particles with 0 EK. Now that makes sense. If there can't be, every particle has to have a certain amount of energy. So even when I get to one particle, it has a very, very low energy, but it cannot have 0 energy because then it's not moving. That's not possible. Next thing to note over here, this graph cannot touch the EK axis again, because if it touches that EK axis, the x-axis, then you're telling me that I have a non-existent particle with a ridiculous amount of energy. That is not possible. So this graph does not extend. Okay, so it doesn't extend. Oh, let's write this so you can read it. It doesn't extend. It has an end point. There's no arrow to this. Okay, it stops. But this point represents a very small number of particles. It has a very high kinetic energy. We're okay with that because not all particles have the same amount of energy. There's an average that we look at. So, what happens if I change the temperature? And in particular, I'm saying what happens if I make the temperature higher? Well, now you look at this and this is going to feel very, very strange to you, because you would expect normally that if I make the temperature higher that you would want the y-axis to increase. But remember, it's not going to. Temperature is about the kinetic energy. So here, that's my biggest number of particles. The biggest number of particles has a bigger kinetic energy, so the temperature is higher. However, the area under both these graphs, the area is constant. It must be, because I have the same number of particles. It's the same system. Okay. Now, what I didn't do over here, all right, is I didn't talk about this. This point there is my activation energy. All the particles to the right have enough energy for the reaction to happen if they collide in the right way. All the particles to the left don't have enough energy. So even if they collide in the correct orientation, it actually doesn't matter. All right? So this area is very important, and that area will tell me whether the reaction is fast or slow. If I go back here, my activation energy doesn't change just because I've increased the temperature. But what does happen is this graph is now ended higher than the last one did. So before I increased the temperature, this was only the area of particles that would collide. Now I've increased the temperature. Now all of these particles have enough energy. So now I have more particles. I have more particles that have sufficient energy. So I'm more likely to have an effective collision. Okay? So if the temperature is increased, more particles will have a higher EK, which means there's a greater number of effective collisions per unit time. This little statement, per unit time, you are going to see it over and over again. It is very, very, very important when we talk about how these reactions happen. All right? So, what happens when we add a catalyst? Well, when we look at the fact that a catalyst lowers the activation energy, it increases the number of effective collisions because, first of all, a catalyst changes this. It doesn't change the energy of the reactants, doesn't change the energy of the products, doesn't change delta H. But it does mean that the value of the sufficient energy gets smaller. So, what it does is this. Here was the original activation energy. We only had this little number of particles that could bond. Now I move it to the left, so an activation energy moves to the left on this Maxwell-Boltzmann distribution curve. And now I'm adding in all of those particles that now have enough energy. The reaction will go faster because I have more particles that will have that minimum energy or more. Okay? Very important things to note about a catalyst. Number one, they do take part, but they emerge unchanged. They have to take part, otherwise what's their point? What's the point? But by taking part, they create, and this is what they're saying, let's not go there. They create an alternative path for the reaction. They help with the correct orientation in some ways, but they do lower the activation energy, which is very, very, very important, okay? They do not cause a reaction to take place that would normally take place. Okay, they can't make a reaction happen. They can only make a reaction that would happen at some point, that can happen, go faster. Okay, so they're not going to, so you can't put a catalyst into a reaction with the noble gases and go, there you go, off you go, have a nice time. The reaction's still not going to happen. Okay, it doesn't matter. Catalysts function by creating an alternative path, which you've seen in the energy profile graphs. Catalysts do not change delta H, which I told you as well, and they do not affect the amount of product formed. They only affect the speed. Please be careful here. You're going to be very tempted to tell me that it changes the product. They are going to catch you out with how catalysts work. So, you please now need to do activity 1 on page 207, question 3 and 4 in particular, and the memo will be on Teams for you. And that's where we're going to end for this video, and we'll do the next section in the next video.